The choice of academic major is a pivotal decision in a student's life, influenced by a complex interplay of factors such as personal interests, aptitudes, and external influences. In Indonesia, secondary school students typically choose between the natural sciences (IPA) and social sciences (IPS) tracks, a decision that significantly impacts their future academic and career paths. Previous research has explored the prediction of students' major choices using various machine learning algorithms, with naive Bayes being a popular choice. While some studies have reported exceptionally high accuracy rates, these results often warrant careful interpretation due to potential overfitting issues. Overfitting occurs when a model becomes too closely tailored to the training data, leading to poor generalization performance on unseen data. Moreover, the prevalence of class imbalance, where one class, for example, IPA, is significantly more represented than the other, for example, IPS, can further exacerbate the challenges of building accurate prediction models. To address these limitations, this study focuses on evaluating the effectiveness of various techniques for handling class imbalance in improving the performance of naive Bayes models for predicting high school students' major choices. By mitigating the effects of overfitting and class imbalance, this research aims to develop more robust and reliable prediction models that can provide valuable insights for students, educators, and policymakers. This research aims to evaluate the effectiveness of implementing class imbalance handling techniques in improving the performance of the naive Bayes model in predicting high school students' major choices and to identify the contribution of these techniques to the accuracy and reliability of predicting high school students' major choices. To achieve these objectives, this research is divided into 5 stages. Data collection. The research utilized data from Manwan College, comprising academic grades in mathematics, chemistry, biology, history, economics, and sociology, as well as students' declared major choices between science, IPA, and social sciences, IPS. This data was employed by the school to determine the appropriate placement of students into either the science or social sciences track. The dataset encompassed a 3-year period, consisting of 586 instances and 7 attributes. The dataset was divided into training and testing sets. The training set included data from the 2021 to 2022 and 2022 to 2023 academic years, while the testing set contained data from the 2023 to 2024 academic year. Detailed information on the dataset, including the number of instances, attributes, and sample data, is provided in tables.
Data preprocessing is a crucial stage in data mining aimed at enhancing dataset quality. Before implementing Smote technique, the first step in preparing the dataset involved checking for any missing data. This process is essential to ensure that data quality is not compromised by gaps that could impact the analysis and final outcomes. The results of this check showed no missing values in any dataset column. Subsequently, categorical feature encoding was performed. At this stage, categorical features in the dataset needed to be converted into numerical format to be usable in the analysis and modeling processes. Encoding is a technique used to transform categorical data into numerical data that can be processed by machine learning algorithms.
The next step involved applying Smote to the training data. This technique generates synthetic samples for the minority class by creating interpolations between existing data points. This process increases the number of instances in the minority class, helping the model learn from a more balanced dataset. New data points in the minority class are generated using the following equation. The following figure illustrates the comparison of instance counts between classes in the training data before and after the application of the Smote technique. After implementing the Smote technique, the next step is the development of the naive Bayes model. Naive Bayes is a probabilistic classification method based on the application of Bayes' theorem, with the assumption of feature independence, given the class. First, we need to calculate the prior probability. Then we calculate conditional probability. With the previously calculated mean, mu, and standard deviation, sigma, values, the next step is to calculate the conditional probability for test data case 1 for each feature to determine its class. The calculations are performed using the following equation. Based on the calculations above, the probability value for the interest in IPA4 test data case 1 is 5.7 times 10⁻75.7 times 10⁻7, while the probability value for the interest in IPS is 9.8 times 10⁻99.8 times 10⁻9. With the higher probability value for IPA compared to IPS, it can be predicted that the student with these attribute values is likely to belong to the IPA label. The results of the study indicate that there is no significant difference in the performance of the model using Smote compared to the model not using Smote. Both the Smote model and the non-Smote model achieved an accuracy of 100%, an F1 score of 100%, and a recall of 100%. This suggests that the Smote technique does not provide a significant performance improvement in this case. Based on the analysis conducted, it can be concluded that the application of the Smote oversampling technique on the studied dataset does not result in a significant improvement in the performance of the major choice prediction model. This finding indicates that other factors, such as the selection of relevant features, hyperparameter tuning, and model complexity, have a more dominant influence on prediction performance. Several recommendations can be made for future research. First, a more in-depth feature analysis